Okay, so just quick reminder that homework 10 will be due Friday, so I extended like one more day. So hopefully that will give people a bit more time to catch up. And so after today, I'm going to, depends on how far we cover. So then I'm going to post the homework 11. And since I postpone kind of like extended due date for homework 10, so I'm going to do it the same thing for homework 11. And since I would expect that today I will be able to start the section 6.1, the eigenvalue, but I will need a little bit more time to wrap it out on Tuesday. So of course, like over the weekend, you should start working on some of the problem on 6.1. But then I will do a couple more examples on Tuesday that will help you to work on the homework as well. So that's why I think it's better for me to just extend the homework 11 to Friday. And over the weekend, I'm going to post the announcement for the exam. And so I think I mentioned this on Tuesday. So final exam will be accumulative and will be at least 50% will be on the new material, which means the new material like covered or learned after the second midterm. And it's going to be up to including the 6.1. But I will be, when I make the announcement, I will be very specific that I will only cover, like for example, in the final exam, I will only test specific cases like in 6.1. Like I will be like more specific about the section 6.1. Okay, so today our plan would be the following, that we're going to finish up the second half for the 5.2. So 5.2, we actually talk about orthogonal subspace, right? So on Tuesday, we discussed you have two subspace, and if every vector coming from one vector space is perpendicular to the other by checking the scalar product or dot product. If the scalar product is 0 for any vector, like between any vector from say X and any vector from vector space Y, then we say these two vector space are orthogonal. But we also talk about another a little bit stronger concept, which is the orthogonal complement. So orthogonal complement means, okay, you give me a vector space X. I want to be able to collect all the other vectors in the space such that it's orthogonal to every vector in X. So you can imagine the orthogonal complement, it's actually, the collection is larger, right? Because we need to collect all the possible like perpendicular vectors out there. So there are two different concepts here. And then we kind of switch the gear to the following things, that it turns out that there are two spaces which are orthogonal complement to each other, and it's closely related to the matrix, or actually to the system of equation. So this is the thing that I just started on Tuesday. So let's recall some of the things that the very last thing we have done on Tuesday. So we have a general m by n matrix, right? So if you consider the system that we want to solve, AX equals B, right? And if we denote AI to be the ith column of the matrix A, then we can actually say that, okay, then we can write, we already know that this is actually somehow from the exam 1, that A times X is essentially the same as the linear combination of the columns of A, right? So if you use A times X, and then if your X is just basically X1 to Xn, right? Then A times X is really the linear combination of all the columns vectors of A, right? So in this case, if we agree on this, then solving AX equals B, or in other words, if you want AX equals B to have a solution, right? If the system, you want the system to be solvable, then that means, in other words, B should be a linear combination of column vectors, right? Or in other words, then B should be in the column space of A, because column space of A is really just the collection of all the linear combination of column vectors, right? Or you can say the span of all the column vectors. So if you want AX equals B to be solvable, then B should be in the column space of A. So that's essentially kind of connect the order concept with something we learned in 3.6. Then on Tuesday, the very last thing we defined was this range of A. So range of A, we denoted R of A. So I mentioned this last time that do not confuse this notation with a rank, right? Rank is different. Rank is the number, it's a number, right? So we will use RANK of A, right? But here, range of A is a subspace. So it's a space, it's a collection of vectors. And what range means? Range means that I'm going to collect all the vector B such that B equals AX is solvable, which means that B can be represented as A times some vector X. If you think about it, if you want to collect all the possible B such that B can be solved as A times X, then if you rephrase it, that means you want to collect all the possible linear combination of the column vectors of A. Then actually it turns out that we can check that the range of A is nothing else but just the column space of A. They are equivalent. So whenever you see the range of A, you can directly, later on we're going to see an example, we can directly find out what the column space of A is. Then we can know what range of A looks like. Maybe you can find a basis, or maybe you want to express it as a span of some of the bases, something like that. We can definitely explicitly solve it, right? Because we already know how to solve for the column space in 3.6. And it turns out that as an application for orthogonal, right, concept, we actually find out that this range of A is orthogonal to another space which is close related to the matrix A. So we're going to essentially now take a look at, investigate a little bit more about the null space. Okay, so what's null space, right? So we have seen this before. This is actually in, I think, 3.2, I think. So that's the first time we see the null space. So null space is just the collection of all the vector X such that A times X equals 0, right? So you're solving or collecting all such X, right? So now I want to do a little bit more in-depth investigation about what the equation looks like, or what this solution looks like. So we just write out, literally expand the whole thing, right? So we want to solve AX equals 0, right? So we really write down all the entries in A, right? So this is really just the AX equals 0. I just write down the whole system of equations. So I kind of expand it, right? So now you can see that X is really just X1 to Xn, right? And all this small A11, A12 is really just each entry of the matrix A. But now instead of writing down like this, I want to represent each equation as the scalar product, right? So, or matrix multiplication. So you can see that the first equation, right? You can rewrite it in terms of the column vector, the row vector, right? This is the first row of A, right? You will see that the first equation looks like as if you're taking the first row of A multiplied by the column vector, right? By the column X1 to Xn, right? So this is actually X, right? So, or you can actually say you're doing the scalar product, right? Of the first row with the vector X, right? So you're doing this multiplication here. And that's essentially just the rephrase of the first equation. And you want this to be 0, right? And you can see the second equation, as you can imagine, will be looks like the second row times X, right? And you do all the, so basically this M equation here looks like the last one would be the last row of A multiplied by X equals 0, right? So basically this tells us if we want the vector X to be in the null space, then all these vectors should be perpendicular to each row of A, right? So this is the upshot. This is the very important observation here. So it turns out that if X is in the null space, then every single row of A is orthogonal, or you can say perpendicular, right, to every X in the null space, right? In other words, if we want X to be in null space, then this vector X should be perpendicular to every single row vector of A. But now I want to rephrase it because I want to relate this with column space. So if you think about it, every row of A, right, it would be the same as column of A transpose, right? So you first do the transpose, right? You flip the matrix, then the column, the row will become the column, right? So when we talk about row vectors of A, will become column vectors of A transpose, right? So just rephrase this observation again, then we essentially derive the fact that then every column vectors of A transpose should be orthogonal to all the vector in the null space of A. So in some sense, we are kind of now comparing the two subspace between two different metrics, right? One is the A, original A, one is A transpose. So now what now, right? So we know now, okay, every columns of A transpose should be orthogonal to all the vector from null space of A. We can even do a little bit further. If I know every column of A transpose is orthogonal to X, then it should be the same. It does, because when we do the scalar product, it's a linear process. So it should not affect if you take a vector, which is a linear combination of columns of A transpose, right? So if individual column vector is already true, which is orthogonal, then any linear combination of those columns of A transpose should also be orthogonal to X, right? So when you do the scalar product, you can calculate like one by one, right? So now what does this mean? Up to here, then if you know every linear combinations of columns of A transpose is orthogonal to all vector from null space of A, then this is really nothing else but the collection of all the vectors in column space of A transpose, right? So then this basically just tells me that, okay, any vector which looks like linear combination of columns of A transpose, which is any vector from the column space of A transpose, should be perpendicular, or you can say orthogonal to null space, right? So right away, we derive this very important concept that we know that the column space of A transpose should be, as a space, should be orthogonal to null space of A. And to relate back to what we just saw, what's column space of A transpose is really just the range of A transpose. So basically, you can say that the range of A transpose is orthogonal to null space of A. So you have a vector from null space of A. It should be perpendicular to any vector which is from, you can say the range of A transpose, or you can say column space of A transpose. They're the same thing. Okay, so any question so far? Okay, so now I want to draw this picture to indicate what we just saw. So this is just a sketch. Like it may be a little bit misleading in the sense that like my picture is restricted to 3 dimensions, right? So you need to keep in mind that these things should live in like a higher dimension, right? It could be true for Rn, but I'm just trying to draw a sketch to indicate that where the things are lies in, right? So first of all, you should think of that, okay, how would you think of a matrix A, right? So you can have, say, this is Rn, right? And you have a vector X here. Say, if you multiply by A, it will give you another vector in Rm, right? So this is, say, Y, right? And Y equals A times X. So you can think of A as a mapping, right? You give me an input vector X, then output Y, right? And it's from, because A is M by N, so it's actually from Rn to Rm, okay? So now, in other words, you can also think of A transpose as a mapping, right? So A transpose would be actually from the other direction, right? So A transpose is going to map some other Y vector from Rm, right? Because now you flip the dimension of the A, right? A transpose is M by M. So the domain should be Rm, right? From the image back to the domain. So you will map to here some other vector x here. So now what this picture should look like. So where is null space, right? Null space is the collection of all the vectors in the domain of A such that it's going to solve Ax equals 0. So you can imagine that, okay, I'm going to have some like vector space, right? This would be my, like some subspace. This will be my null space of A. And where the range of A transpose lies in, right? So range is you're collecting all the possible image, right? But A transpose as a map is from Rm back to Rn, right? So the image should also lies in this Rn space, right? But then now if we want to visualize it, it should be perpendicular to null space, right? So in this case, maybe that's just draw a line, right? Or I mean, technically it should be some like maybe higher dimension, right? But it's perpendicular. So this is like range of A transpose, right? And the range is usually lies in the image of your mapping, right? So you can see that why this picture makes sense in the sense that the null space and null space of A and range of A transpose, indeed, they live in the same space. You cannot compare two space which lives in a different space, right? You cannot compare something from Rm to Rn, right? Because they have,
I'm a little confused here. So you're showing that you're using A transpose to reverse what you got for the y vector, right?
No, not
where
reverse. It's not inverse. It's not inverse map. It's just, I'm just saying, maybe I should.
I'm confused.
Yeah. It's not inverse, but it can map something from Rm back to. It's just imagine this is another map, but the domain for A transpose is now in Rm. So it's not necessarily the exact inverse map, but the domain is actually sitting in Rm. So I should think of that. Oh, maybe there's another maybe vector here. Maybe I call it Z. I want to maybe U here, right? And then you go here to A transpose times U, which is my V, right? It's not inverse, but the domain is the same as Rm. So essentially yeah, so it's not inverse. Actually, this is a good question. This is not inverse. They're not necessarily inverse. But essentially what I want to use this diagram is to show that because now A transpose is M by M matrix. So you should input a vector from Rm here, right? And this is the domain of A transpose. So if you want to check where the range of A transpose lies in, it should be here because range is collecting all the possible image, right? So then you can see that that's why I draw the picture where range of A transpose lies in this space Rn, right? And it has to be perpendicular to the null space because this is what we essentially derive. Then you can imagine if that's the case, we can just swap the role of A and A transpose, right? So up here in Rm, this space, you should also have a similar relationship, right? If you just swap the role of A and A transpose. So you could actually imagine that you could possibly have, say, a null space of A transpose, right? Now it should be here, right? Because it should be in the domain of A transpose. So you might have, I don't know, like some range of, the null space of A transpose, right? And now you can check with, it should be perpendicular with the range of A, right? And range of A lives in the image of A, right? So you could have this dual relationship, right? Because you just simply swap the role of A transpose. So this picture is just to indicate that where all those space lies in, right? And how this A and A transpose map works as a, as a linear map, for example. So now because of this, we actually have something even stronger. Here, we only say they're orthogonal to each other, right? But it turns out that we have a stronger conclusion in the sense that they're not only just orthogonal to each other, they should be orthogonal complement to each other, right? So this is actually stronger. So this is actually what we call the fundamental subspace theorem. So if you have n by n matrix A, then it turns out that the null space of A is the orthogonal complement of the range of A transpose, right? So being orthogonal complement is stronger than just being orthogonal, right? And once you swap the role of A and A transpose, then you also have the same thing, but with different metrics, right? So now we also know that the null space of A transpose should be the orthogonal complement of range of A. So we have mutually have this nice relationship here. Okay, so here, the picture here, what I want to say is that the range of A would be perpendicular to null space of A transpose. And here we have range of A transpose would be perpendicular to null space of A. Okay. Okay, so now before we show more example or do some computation, I want to do a little bit theoretical theorem to show you that why it's nice to know about the orthogonal complement. So from the definition, from the terminology, right, complement means everything else in some sense, right? So it turns out that if you have any subspace in Rn, right, if S is just any subspace, then it turns out if you check the dimension of the subspace S plus the dimension of your orthogonal complement, then it should add up to the total dimension of your ambient space, right? So you have a subspace sitting in Rn. So the largest dimension should be N, right? That's where you sit in. But then it turns out that we can show that the dimension of S plus the dimension of the complement should add up to the dimension of the total space, the largest space, right? That actually kind of tells you that why we called it complement, right? It's everything else. So it turns out that the complement is not only it's perpendicular to your orthogonal original space, it will actually kind of add up to the whole space Rn, right? So even better, if this is the case, if you could find, say, the basis for S, right? Say U1 to UR. So that's assume if dimension of S is R, and you find another basis for the complement, that means you have dimension n minus R here, right? So if you could find a subspace and its orthogonal complement, and you find the spaces for each space, then you could put it together. Those vectors, it's going to form a basis for the largest space. So sometimes that's why instead of finding the basis for the whole space all in once, what we can do is find a basis for a subspace, and we find a space for its orthogonal complement. Then we put it all together. Then that will be the basis for my whole space. So that's also an advantage, because sometimes that maybe your largest space is like hard to find, right? And then it also depends on which basis you were thinking about, right? So sometimes there's an advantage of knowing the orthogonal complement. And in linear algebra, there's also an important concept that we mentioned, and you might actually see it later on in some other literature. This is what we call the direct sum. So it turns out that orthogonal complement has a very direct relationship with this, what we call the direct sum. So direct sum means if you have, okay, the ambient space is W, and you have a two smaller subspace U and V, right? So let me put it here. So U is in W and V is also in W. They're all subspace. And if you know that each vector from the ambient, the largest vector space W, can be written as a unique decomposition like this from U and V, then we say W is a direct sum of U and V. So it's not just sum, right? Because if we can do the decomposition, it's just some summation. But direct sum especially means that this decomposition should be unique. Meaning, if you can represent W in terms of another vector, say U tilde plus V tilde, and two vectors, and those two vectors also from each of them, either from U and V, right? If you can find another two vectors, U tilde and V tilde, such that W equals the sum of those two, then because we say that it's unique decomposition, then this means U has to be the same as U tilde, and V has to be the same as V tilde. That means when you decompose when you decompose the vector W into a summation of one vector from the vector space U, one vector from the subspace V, the way you do this decompose is unique. There's no other way, right? You could decompose it. That's what I meant by unique decomposition. If that's the case, then we say W is the direct sum of V, U and V, direct sum of U and V. And we use this spatial notation like a plus with a circle. It's the essentially pretty much the uniform notation that people use for direct sum. So why we care about direct sum? It turns out that if you could find a orthogonal complement of a subspace, then the subspace S and its orthogonal complement will form a direct sum of the ambient space. So this is essentially, that's why we also care about the orthogonal complement. So once you find orthogonal complement of a subspace, then it's going to form the direct sum of the ambient space. So basically, if you have S, which is a subspace of Rn, and S will lies in Rn, right? And the orthogonal complement will also lies in Rn. Then it turns out that you can decompose any vector, say W from Rn, into a unique decomposition of something from S and something from its orthogonal complement. And now if you think about it, this essentially, in some sense, it's related to what we did before, that you did you can decompose a vector into orthogonal decomposition, right? Because now in this case, not only W can be written as X plus Y, but since X is in the subspace S and Y is in orthogonal complement, so we also know that X will be perpendicular to Y, right? So you can see that this is a very, in some sense, very spatial decomposition. And I want to show you an example like this, right? So R3 can be decomposed into, if you call this span of E1 to be S and span of E2 and E3 to be orthogonal complement. We've seen this before, right? And in the picture, if this is XYZ in R3, right? So what span of E1? Span of E1 is just the x-axis, right? So this is span of E1. And we actually saw the example before. If you have such subspace, then the orthogonal complement should be everything that's perpendicular to anything on the line, right? So we can imagine that it should be the YZ plane. It should be like very large, right? Like this is YZ plane. And this is essentially the orthogonal complement, or you can say it's a span of E2 and E3, right? So you can see that any vector in R3 can be decomposed as a vector, right? So you can see that any vector A, B, C in R3, right, can be decomposed into something from span of E1 plus something from span of E2 and E3. And also you can check, right? I want to confirm one thing. What's the dimension of this span of E2 and E3? The dimension is 2, right? Because it's a plane. And dimension of span of E1 is just 1, right? And you can see the dimension add up to be 3. That also confirms what we saw before, right? The dimension of the space, some subspace, plus the dimension of its orthogonal complement should add up to the total space. So you can see that either way, by drawing the picture or using some algebraic point of view, you can see some insight here. Okay, so the last thing I wanted to say that regarding this before we see the example is that this is kind of trivial in the sense that if you do the if you already have orthogonal complement for some subspace, you do orthogonal complement again, right? Then of course it should go back to itself, right? So this is true for any subspace. And now the only the conclusion we get from this part is that because we know that we already know from the previous theorem that the range, or you can say the null space of A, is orthogonal complement of the range of A transpose. We also have the null space of A transpose is orthogonal complement of range of A. So we know that because they're orthogonal complement to each other, they should form the direct sum. So the last conclusion is just say, okay, the Rn should be able to written as a direct sum of these two space. And you also have Rm, right, which is the other space. Rm should also be the direct sum of null space of A transpose plus now range of A. And this is under the assumption where A is M by M matrix. So this is a little bit theoretical here. So I mean, this is some insight I think is necessary, especially for like people in math major, because later on they're going to see this kind of thing in more advanced class. So now I want to definitely do like some computation here. So I have a, this is 2x3 matrix. I want to find the basis for null space of A, range of A transpose, and also null space of A transpose and range of A. And then after I explicitly find the space or the basis, essentially, I want to confirm all the things I just said above. First, are they really like orthogonal to each other, right? We know that this two should be also, not this two, yeah. This two should be orthogonal to each other. This two should be orthogonal to each other. Once I explicitly find out what the space looks like, I want to confirm that. And also I should be able to draw a picture to see like more insight, right? What they looks like, okay. But just the fact to find a space, you already know how to do it, right? I mean, I believe by now everyone should know how to find a null space of some matrix. What about range? As we discussed, range is just a column space of some matrix. You already know how to find a column space, right? So in some sense, to find the space itself is not new, right? The techniques, you already know about it. And if you think about it, all we really need to do is to do Gauss elimination, right? You want to simplify, reduce it to REF, then we're pretty much halfway there, right? So now let's just do a quick computation for the simplification, right? So I want to take 1 and kill this 2 here. So 1, 3, 1, 0, minus 2, minus 2, right? And then I'm going to simplify this row by dividing minus 2. So this will be 0, 1, 1. Okay. I want to reduce to REF, so it will be easier for me to solve for the null space. So in the end, I will have 1, 0, minus 2, 0, 1, 1. Okay, so this is REF of A, right? So now from here, I can directly solve for null space, right? So I'm solving null space, meaning I need to solve AX equals 0. So I want to see exactly what the solution looks like, right? So in this case, let me see. So X3 is the free variable. Okay, then X2 will equals minus X3, which is minus alpha. And X1 is 2X3, which is 2 alpha. So my X should looks like 2 alpha minus alpha and alpha, right? So in this case, you can see that you can factor out alpha, and this will be 2 minus 1 and 1. So alpha can be any number, right? That's the free variable. So we already know from here, right? This is something you already saw before. Then null space is essentially the collection of all the vector X, which looks like span of one vector, right? Because it's a linear combination of one vector. So this is a span of this one vector, right? If it's a span of one vector, geometrically, it looks like a line passing through this vector, right? And as you can see, it's a subspace in R3, right? It's a line in R3 because it has three coordinate, right? So now so either you can tell me the null space of A looks like span of this, or you can say the basis for null space is just this one vector, right? Either you tell me what does it looks like as a span, or you tell me what the basis is, right? Depends on what the question is asking. Now, what about range of A, right? Because now I find null space of A. But since we are with the matrix A, so I think it's easier for me to check the range of A at this point, right? So what's range of A? Range of A is really the same as column space of A, right? Then column space of A, in order to find what the basis is, remember we need to pick out what the pivots are, right? And where if the columns that with the pivots are the one that's linear independent, right? So basically, first, we know this is the first thing we found here. Second thing, I want to find range, right? So this is range of A. But range of A is really the same as column space of A, right? And from the REF, I know that the first and second columns of A are linear independent. So they should give me the basis for the column space, right? So the column space of A should be the span of the first two columns. And remember that back then when we deal with 3.6, when we want to find the basis of column space, we should use the original column, right? Because the pivots here only indicating that which columns are independent, but the column space of the REF may not necessarily be the same as column space of the original matrix. So you should pick up the original matrix here. So this will be 1, 2, and 3, 4, right? And this is essentially the column space of A, which is essentially the same as range of A, right? Or as I said, you can say the basis of range of A is just these two vectors. Either you tell me as a span what the space looks like, or you tell me the basis. And it's a span of two vectors with two coordinates. So it should be a subspace lies in R2, right? You only have two coordinates. So I want to emphasize this because later on I need to compare with things in different space. So then we found the column space. Actually, you can see once you have the REF, it's not really a big deal because, I mean, this is just, you already have everything you need. Now we change the gear to A transpose, right? So now this is done. Now we need to find null space of A transpose and the range of A transpose. So now let's see. So what's A transpose, right? So A transpose, let's really do the transpose, right? Just flip it. Flip the matrix. Now to find the null space, do the same thing, right? Simplify it to REF. So I have 1 and kill this. So this will be 1, 2, 0, minus 2, 0, minus 2, right? And this will be, I want to take the row 2 times minus 1/2 and row 3 times 1/2. So this will be 1, 2, 0, 1, 0, 1. And eventually I can cancel out this. So 1, 0, 0, 1, 0, 0. So everything is nice like this. Okay. So this is the REF of A transpose. Now I can solve for the null space of this matrix. Right, so let's see. So I only have 2 pivots here, right? So be careful, right? Because it's transposed, so you can see that the dimension flipped. So I have actually, this is x1 equals 0, x2 equals 0. So unfortunately or fortunately, we know that there's only one solution for the null space, which is the origin, 0, 0, right? Because I mean, from this REF, we can see that, I mean, it's actually a unique trivial solution. So this tells me the null space of A transpose is really just the 0 vector in R2. Okay, this just happens to be the case, right? So this is the, like, it may be like this, right? It really depends on the matrix. It's not always that the null space would be 0, right? but it just happens. And what about range here? Range of A transpose, right? This is range of A transpose. And this will be the column space of A transpose, same thing, right? Then you can see that this is just span. I mean, this is the first column and second column are linear independent, right? So we need span of first column and second column. I'm being a little bit quick here because I assume people already know how to solve the basis for the column space, right? And so you can see that this is really, I need to use this the original columns, right? And this is a subspace in R3. Okay, this is a two-dimensional subspace in R3. So now you can really explicitly solve everything, right? We solve the null space of A transpose, range of A transpose, and we also solve the null space of A and range of A, right? So we have 4 spaces here. So I really want to check that the null space of A, for example, is perpendicular to range of A transpose. I really want to check they're mutually perpendicular, right? So first thing I want to check, null space of A is perpendicular or orthogonal to range of A transpose, right? So let me let me copy. So null space of A is span of 2 minus 1 and 1, right? So null space of A is span of 2 minus 1 and 1. Right, and I want to also recall range of A transpose is what we just find out here. It's span of 1, 3, 1 and 2, 4, 0. Right. So first you can observe is a range of A transpose the same? The range of A transpose the same as the row space of A, exactly. Yeah. So you could actually, this is a good question, right? So essentially, in some sense, technically, you don't technically have to do the A transpose literally. You could actually, if you know, or if you're comfortable thinking range of A transpose as the row space, right? They're the same thing because columns of A transpose is row of A, right? Then you could actually stick with the row space and find out what's the range of A transpose. Yeah, you can actually, you don't necessarily have to like do the transpose, but you can also do it directly with the transpose. It doesn't matter, right? I mean, either way, it's just a different point of view. Okay, so now you can see that first of all, it makes sense to compare these two space. Actually, I need a little bit more space. Give me a second. Let me push the things a little bit down here. So it makes sense to compare those two, right? Because they're both subspace in R3, right? So it actually makes sense first to compare these two. But I want to confirm that it's really perpendicular to each other, right? So you want to check any vector coming from the null space. So any vector coming from null space of A, which looks like span of 2 minus 1 and 1, right? So I'm going to have 2 alpha minus alpha and alpha, right? Any vector from null space of A will look like this. I want to check that it should be perpendicular or orthogonal to any vector coming from here. So it should look like the linear combination of 1, 3, 1 and 2, 4, 0, right? So this is, you can call this the vector Y, and from the range of A transpose, right? So you want to say that these two vectors, right, should be true, should be orthogonal to each other, right? This condition should be true, right? So we want to check x dot y equals 0 for any vector x, which looks like 2 alpha minus alpha and alpha, and any y like this. This is extra checking, but I think this will provide some insight. So, okay, so now let's see, right? So I really literally just do the dot product. So I have 2 alpha times the first thing is A plus 2B, first coordinate, right? and plus minus alpha times 3a plus 4b, and plus alpha third coordinate times a plus 0. And you can actually check this is going to be 0 after the expansion, right? So I have 2 alpha a minus 3 alpha a and a alpha, right? So this will cancel out, and you have 4 alpha b and minus 4 alpha b. So this is indeed 0. So you really show algebraically that any vector from one space, null space of A, is perpendicular to any vector from range of A transpose. And as you can see, this also makes sense in terms of the space. This is a one-dimensional space. This space is 2-dimension, the range of A. So they add up, the dimension will add up to be 3 because they live in R3. So geometrically, what should looks like, right? So range of, this is R3, right? So range of, this is not necessarily some XY plane, but it's some plane, right? So that's say maybe a little bit tilted. This is range of A transpose. And what's your span of, what's your null space, right? And the null space should be perpendicular. So you will have a perpendicular line, right? So this is span of 2 minus 1 and 1, which is my null space of A, right? And this is a span of some 2 vector here, right? So you can see that geometrically it will be some plane, right? That's the span of 2 vector. That's your range of A transpose. And you have a orthogonal complement, which is a 1-dimensional thing. And it add up to be a 3-dimensional thing because it's R3, right? So you can see from geometric point of view and also algebraically, you can check that as well. And that confirms our answer is really correct in some sense, right? But then what about the other one, right? So the other one is null space of A transpose, right? And I want to see this would be the case. But this is actually a little bit trivial because one of them is 0. So remember that the A transpose, the null space is just 0 vector in R2, right? And range of A is actually the span of 1, 2, and 3, 4. This is what we calculated. So it's also a subspace in R2, right? So geometrically, what does it look like, right? So this time I want to do a geometric picture first. So because now they're all in R2, so we only really have R2. One of them is just the origin, right? The other is the span of 2 vector, but you have a subspace, which is 2-dimension, but you are in a 2-dimensional space. So actually, you can see that in this case, it will also be the whole R2. So this thing would be your range of A. And the green one, just the origin, is the pool null space of A transpose. So if you're comparing 0 vector with anything else, and of course, 0 vector will always be perpendicular to any other space. This is kind of the most trivial situation, right? So we know that this is kind of trivially true. Or you can, another word, you can say a 0 vector in R2, right? It will always be perpendicular to any vector, which looks like a linear combination of this, right? But of course, if you take a 0 vector dot product with anything else, it's always 0, right? So there's not really that interesting. But I want to also check dimension-wise, right? If you only have 1 0 vector, it's a subspace of 0 dimension. And you have span of 2 vector dimensions 2. You add up together will be 2 because you are in R2. So that dimension-wise, it also makes sense, right? So, I mean, I do all this checking is hopefully want to give you a little bit more insight into the space, right? I don't want people just to blindly memorize what the calculation is, but I want to be able, I want everyone to be able to see beyond that. Can you visualize it, right? Algebra, can you check it? Okay, so any question so far?
I had a question on,
Yeah.
because I think I missed something. I thought the first perpendicular test that you did was in R3.
Yeah.
So how then did we get with the second perpendicular test in R2?
Oh, because they're in the different space, right? Because remember back then I was saying that those two are lies in different space, right? If you go back to the diagram here. right? The null space of A and range of A transpose, they're living in Rn. In this case, our Rn is R3. But the other space, when we swap the role of A and A transpose, then they're living in Rm. They're not necessarily living in the same space. So for example, in this case, right, like you can see that A is 2 by 3. So if you think of it as a map, then A is actually mapping from R3 to R2. That's why the null space should living in here, right? And the range of A transpose. And R2, you have what we saw here, right? The 0 and the whole thing. Yeah, so they're actually might living in different space. In general, they live in different space because the dimension, it also depends on what's A, right? In this case, it's 2 by 3. So one of them will be R3, one of them will be R2. That's why I draw those diagrams to emphasize that one of them living in the domain, one of them living in the image. Yeah.
Got it. Thank you.
Yep. Okay. So so actually, there's another. Actually, I want to let me see. Okay. So I want to later on come back to like one last example of this section, but I want to later on be able to do it as a review. So I want people to think about like to catch up with this section. And because of the time being, I want to move on to the eigenvalue and eigenvector, because for now, you should have most of the things for the 5.2, and you should definitely be able to solve most of the problem. And but coming back maybe next Tuesday or Thursday, I will definitely do a couple more questions as a review from each of the section. So there will be one problem I want to leave it till there, or maybe next Tuesday when we have a little bit more time. And I want to do kind of like a mix and match, because if I just keep going on 5.2, then while everyone hasn't really catch up or study 5.2, then all the things I said may not necessarily make sense. So I want to wait it until next Tuesday. Then I could do a little bit more to reinforce the concept here. Okay. So now I want to move to 6.1, which is essentially what I promised, the eigenvalue and eigenvector. So this might sound weird or complicated, but again, actually you will be surprised that once you know what's the definition for eigenvalue and eigenvector, the techniques of solving it is, we have already seen before. You can actually convert the problem of finding eigenvector and eigenvalue into, especially eigenvector, for example, into solving the null space of some matrix, and that's it. So, but then to find eigenvalue, you need to solve some kind of polynomial, like a projected polynomial or some like a third-degree polynomial. Once you'll be able to solve the root of polynomial, that will give you the eigenvalue. Then based on this eigenvalue, you want to form some matrix, as you can see in a minute. Then you are going to find a null space of some matrix. So this basically tells you, as you saw now, that all we have done here is all related to first looking for the REF of some matrix, then identify the null space, then maybe find the column space or row space of a matrix, right? All these things, you need to know how to do this in order to be able to solve some application, right? So if at this point you don't feel comfortable of finding the null space or column space, something like that, then you should be careful, because this is essentially will carry on till like 6.1, right? Section 6.1. Okay, so let's get to the main topic. So what's eigenvalue and eigenvector? Let's first take a look at the definition. So because later on we are going to talk about or use determinants, so we can only talk about we're going to focus on the n by n square matrix. And eigenvalue, I mean, from the name, it's a value, or it's a scalar number essentially. So we use lambda for eigenvalue. Okay, this is kind of like a convention that mathematicians use all the time. So this number is called eigenvalue of the matrix A if you can find a non-zero vector x such that x, in this case, because it's n by n, so you can imagine x will be in Rn. You can find a non-zero. It has to be non-zero. I need to emphasize this because I don't want to see people later on give me a vector, zero vector as an eigenvector. Okay, so eigenvector should not be 0. So it's non-zero vector. So if you can find a non-zero vector x such that a times x is this lambda equal to lambda times x, then we say this lambda to be the eigenvalue of matrix. And this corresponding non-zero vector x associated with this lambda is what we call the eigenvector associated with lambda. So you can see that if you change the eigenvalue, your vector might change, right? So one eigenvalue will corresponding to some eigenvector, right? So based on this definition, let me show you right away what's the example. So I have this matrix A, 4, -2, 1, and 1. And of course, to find the eigenvector, it's not that easy, right? And you need to do some work, right? But here I just tell you the result first to just show you as an example. So if you have a vector which is 2, 1, right? Then if you multiply a times x, just directly do it, it actually equal to 6, 3. But you will observe that 6, 3 turns out to be a multiple of x, right? X is 2, 1. So you can see that now you really have a non-zero vector x, which is 2, 1, such that a times x is equal to some value, some scalar times x. And in this case, this 3, which is the lambda here, is the eigenvalue. So basically, in this particular example, lambda equals 3, which is one of the eigenvalue of A. And this x vector in particular, 2, 1, is an eigenvector associated with this lambda. So of course, you could ask me, how do I know 2, 1 is an eigenvector of the eigenvalue 3? Of course, I already know the answer. That's why I've just showing you as an example. Of course, if without any advanced information, I would not know for sure which vector would be the eigenvector. You need to really look for it. So before we really explicitly solve this, I want to discuss some of the property. Why, if you have 6, 12, could you, so you can actually see that any if you have this is actually what I'm going to say, the question from Devin. So it turns out that if you find one eigenvector, you actually find infinite many, in the sense that if x is an eigenvector of some eigenvalue, then any non-zero multiple of the eigenvector could also be an eigenvector, right? If you think about it, you can actually check, right? If 2, 1 is an eigenvector, right? If you multiply this vector by 2, for example, right? What's 2x? 2x will be 4, 2, right? And you do a times 2x again, right? Which would be a times 4, 2, right? Then you can do it, then just literally compute it, right? So you can see that this would be 16 minus 4, that's 12, and 6. So this would be another 3 times 4, 2, right? So you can see that if x is an eigenvector, then lambda x, alpha x for any non-zero alpha will also be another eigenvector. So what does that mean? It means that if you could find an eigenvector, then any vector along the same line as this vector will also be an eigenvector. So that's why if you found one, then you have the whole space, which gives you the eigenvector as well. So that's why if you could even find one, then you actually find infinite many, right? So any multiple of your eigenvector would be another eigenvector. So that's quite powerful here. And also another important feature is that why we care so much about eigenvector, because once we know the eigenvalue and the eigenvector, you will right away know how this matrix affects this vector. The effect we already know, right? If you could find the x here, then we know when A acting on x, it will look like lambda x. Then if you multiply by A again, it will be another lambda, right? So for example, I want to draw you a picture here. So you have 2, 1 here, like what we said, right? If you multiply by A, right? Then A times X, we know it's what we just calculated. It will be 3X, right? So 3X would be 6.3. So maybe a little bit larger, right? My scale may not be necessarily correct, but I just want to say A times X is 3X, right? So this would be 6.3, right? So this would be 3X. Now, if you do it again, what will happen, right? Then you multiply by 8 again, right? Then you will have another even longer vector. And as you can imagine, then this will be 3 times 3x, right? That will be 9x. So this would be essentially a squared times x, meaning you take a times ax again, right? So this would be essentially tells you that if you have an eigenvector, each time you multiply by a, the effect is just along the same line, right? Each time it depends on the eigenvalue, right? Here we have 3. So each time you multiply by 3, right? So the effect is as if you're just doing the stretching along the same line, right? But of course, if you have lambda to be negative or smaller than 1, so it might be pointing the opposite direction or doing the compressing, right? Shorter and shorter. But this tells us that the effect under the matrix will always be, like for the eigenvector, will always be along the same direction or opposite direction. So this is actually what I said. The effect of A acting on the eigenvector, you already know that it's always along the same or opposite direction, right? So you can see after you multiply by A, you have 3x. But we know 3x as a multiple of the eigenvector will still be an eigenvector. So you add on A acting on again, then it will still be along the same direction. So once you can, if you think of A as some kind of effect, right, then this tells you that, okay, there's a certain direction. Each time you have some kind of effect, it will resonate, will always having some effect along the same direction, right? So this is, I mean, of course, I'm oversimplified the phenomena, but imagine like if you have some kind of earthquake or like some shaking, and each time you know that it will crack along like a certain direction a lot, right? If next time when the same effect happen, it will crack along the same direction a lot, then eventually this crack will go larger and larger, right? So that's why in some sense that if you can represent a phenomena or some kind of effect by a matrix, then you really want to know what direction that A keep affecting on, right? Then this will tell us that, oh, there's certain direction that which is bad or good, depends on what A is, right? And this also tells us that another feature is that once we know the eigenvector associated to a certain value, then we already know what's A times X automatically, right? So it will be a huge advantage if we could use eigenvector as a basis of a space. If we can use eigenvector as a basis, then we already know what A affects every other vector, right? Because every other vector is just a linear combination of eigenvector. If that could be possible, then we will know exactly how A acting on every other vector. So that's why eigenvector has a lot of like significance and importance. So now let's really see how are we going to find the eigenvalue in X, right? So we can actually start from this. So start from the definition. What's the definition of lambda eigenvalue in X? We want to solve AX equals lambda X, okay? But in this case, we want X to be non-zero, okay? That's the eigenvector. So in this case, we want to rewrite the equation into something like this. So you can actually kind of move the lambda X to the left-hand side, but I want to treat it as a matrix. So I can represent it as lambda times identity. And this whole thing I should multiply by X, right? Then if you do the distribution, then it looks like AX minus lambda X. Then this is actually, I want this to be 0. Let's call this equation star. Okay. So basically this tells us that if lambda, so basically this tells us lambda is an eigenvalue if this equation has a non-trivial solution, or you can say non-zero. solution x, right? In order for ax equals lambda x, you need to find a non-zero x such that the star equation can be solved. But now if you think about it, right, if you treat this a minus lambda I as a new matrix, right, then you're essentially solving the null space of this new matrix, right? So basically it tells me that then the solution set, right, the collection of all the null space, right, of this matrix is the eigenvector, right? So basically this is what I want to say here. Then you're collecting all the solution from the null space of a minus lambda I, right? This is essentially you're collecting all the eigenvector, right? So this is what we just see, right? So all the eigenvector x we want here is essentially belongs to the null space of this matrix a minus lambda I. And this is what we call the eigenspace associated to lambda. Okay, this null space of this matrix a minus lambda times identity is what we call the eigenspace. But now I still kind of haven't really tell you how to find lambda. I mean, we already know how to find x as long as we find lambda, right? So how about lambda here, right? So keep in mind that if we want lambda to be eigenvalue, we need the null space to be non-trivial, right? So we need the null space, right? Because we don't want it to be zero vector. So that means for this null space, I want it to be non-zero. But we already know null space always includes zero, but it's the matter of just trivial or infinite many solution in a null space. If we want it to be infinite many solution, that means this matrix has to be singular, right? Remember, non-singular were corresponding to non-singular or corresponding to unique solution. Singular were corresponding to infinite many solution, right? So we want it to be singular. So it has more than just the zero vector. So if it's singular, that means eventually we are solving determinant of this matrix to be zero. Once you can solve this, then you find lambda. Okay, it sounds complicated. This is just how I derive it step by step. It sounds complicated, but it's actually really not once you see the example here. So before we go into the example here, the last thing is how are we going to treat this determinant of a minus lambda I, right? So actually, if you really expand determinant of a minus lambda I, it's going depends on the dimension of the matrix. It's going to be looks like an nth degree polynomial in lambda. So which means that if say a is 2 by 2, then it will look like lambda squared plus like, I don't know, 3 lambda plus 4, for example, right? Like it will be if a is 2 by 2, then it will be a second degree polynomial in lambda. If 3, then it will be lambda cubic lambda plus something like that, right? And this polynomial is what we call the characteristic polynomial. So in other words, to solve determinant of a minus lambda I to be 0, we want to solve this determinant of this, or you can see we want to solve this polynomial to be 0. So this means you're finding the root of this nth degree polynomial. And you can expect if it's nth degree polynomial, it should have, depends on what n is, right? If it's 2, then you should have 2 solutions, 2 roots, right? This is something we saw in calculus or high school. And when we say n roots, it actually really includes repeated roots or complex roots. So I may not necessarily have time to do the case with complex number. If we have time, I will do it as an extra thing, but this will not be included in the exam. But you could technically have repeated roots, right? So for example, if you solve some polynomial, second degree, the answer might be 1 and 1. Then 1 and 1 repeated, this will count 2 roots, right? So this is essentially what we have seen before. Okay, so now let's really see an example so we can really like see how all this works. So let's see, just start with 2 by 2, right? This is the easiest. I want to find the eigenvalue and eigenvectors. So I want to directly say I want to solve determinant of A minus lambda I to be 0. Okay, this is what we just said, right? We want to solve this polynomial to be 0. Now first check what is A minus lambda I looks like. I want to do it step by step. So this would be 3, 2, 4, 1 minus lambda times identity. So you can imagine it's going to be a diagonal matrix like this with lambda in the diagonal, right? Then this is really just 3 minus lambda, 2, 4, and 1 minus lambda. I mean, I'm doing like kind of step by step. If you know like what lambda I looks like, you can probably skip a lot of step here. So now solve the determinant of A minus lambda I, which is really just determinant of this matrix I just found. Okay, which is really, so now you can see that why I said it's a polynomial, right? So you can check, this will give you lambda squared minus 4 lambda plus 3 minus A. So this would be lambda squared minus 4 lambda minus 5. I want this to be 0. So you're really solving a second degree polynomial, right? So then this really needs a little bit algebra here. So this is really just, you can rewrite it as lambda minus 5 times, you need to do the factoring, right? So this tells me lambda would be either 5 or minus 1. So you have 2 eigenvalue corresponding to a 2 by 2 matrix, right? Like 2 roots, right? Okay, so here, if you really cannot see the factorization right away, you should do the quadratic formula, right? Like, I mean, don't waste time on trying to do the factorization if you realize that you really cannot do it, right, in 10, 20 seconds. Then do the quadratic formula to find the root. That's okay. You should get the same thing. So now we know there's a 2 eigenvalues. So this, I would say, I will use lambda 1 and lambda 2. So 2 eigenvalues. Okay. Now eigenvalue is done, right? We have minus 2 and 5. So then I'm going to go ahead and find out what's the eigenspace, right? So first, eigenspace for this first eigenvalue, right? Then eigenspace is really like what we said above. We want to find null space of A minus lambda I, right? In this case, right? So we want to find the null space of this matrix A minus 5I, right? That's the essentially, then if you can find a null space, all the vectors in this null space is really our eigenvector. Okay, so what's A minus 5I, right? So A minus 5I is, let's just do it again. So this is 3, 2, 4, 1 minus 5 times identity. So this is just 3 minus 5, that's minus 2, 2, 4, and minus 4, right? Okay, so I want to find the null space. Okay, this is not too bad at all. This is actually in the multiple, as you can see, right? So you can actually reduce this to something like this. This is my REF, right? So I'm solving the null space. Right, so you can see that, okay, right away I have just one pivot. So this is x2 equals alpha and x1 equals x2, which is alpha. Okay, not too bad at all. So then x would be alpha alpha, which means that it looks like alpha times 1 1. So my null space actually looks like span of 1 1. Right, so now this is the eigenspace of this eigenvalue. And what does this tells you in the end, right? This tells you that now, this is actually important, I'm going to put it. Any vector of the form alpha times this is an eigenvector. Eigenvector of A associated with this eigenvalue, right? So null space is the collection of all the eigenvectors associated with that eigenvalue. So once you solve this null space of this new matrix, then you essentially find all the possible eigenvector and you put it all together as a space, right? So basically, either you can say 1, 1 is an eigenvector, or actually you can say -2, or 3.5, 3.5, as long as it looks like any vector which looks like a multiple of 1, 1, right? So then basically this is how we find the eigenspace, right? Which is as a collection of all the eigenvectors of this eigenvalue. Okay, so I know I still need to solve for the eigenspace for -1, right? The other, sorry, -2, the other, actually, did I say -1? The other eigen value here. So I would so you should definitely start working on this section. And as I mentioned that I will only, for this section 6.1, I will only focus on the real eigenvalue and real eigenvectors. So I will not go to the complex situation. So I will be really specific when I made the exam announcement. So next Tuesday coming back, I will finish up this example and do another example with 3x3 matrix, because 3x3 needs slightly a little bit more work. But as you can see, the process will be the same. So I want people to kind of catch up over this weekend on this eigenvalue and eigenvector. And then I will pretty much wrap it up, this section. I'm only covered like a certain part of this section. So I will wrap it up on next Tuesday. And next Thursday would be the review. Okay. So let me know if you have any questions, or otherwise you're free to go. Sorry for the delay.
Have a good weekend.
You too.
Actually, can I ask a homework question really quick?
Yeah, sure. Which problem is that?
14a and 14.2. I got confused on what it's actually asking.
Okay, 14a. Okay, so linear transformation defined by this. So okay, so it says that you have a linear transformation, right? And the linear transformation is a map, right? It's defined by the following: that if you plug in a polynomial in P3, then you're taking the let me open up another blank page so I can write here. So what they said is that okay, so this is L. So you should think of L as a linear transformation map from the polynomial space P3 to P2, right? Okay, so now, and then this P3, I'm going to use the basis in this order. That's why they call it order basis. So this is the big basis. Let me call it maybe U, something like that. And here, the basis that I'm using for P2 is 2 and 1 minus x. Right? Okay, let me see. So now, for each of the following vector in P3, find the coordinate.
No, that's not the basis, though. That's what confused me.
Oh, why it's not the basis, though?
Because it says ordered basis 2, 1, negative x.
It's 1 minus x.
No, there's a comma in there.
No, it's comma between 2 and 1 minus x, but there's no comma between 1 and minus x.
What? I see a comma right there, though, in both.
So it's 2 and 1 minus x.
No, there's a comma in between the 1 and minus x, so that's why I'm confused.
Oh, really? My version doesn't have it, though. That's weird.
I don't know why mine does.
Huh.
I've seen a couple of typos in the book before, so I don't know.
Yeah, it might be, because if you think about it, right, P2 is a dimension 2 vector space. You should only have 2 vector as a basis, right? It doesn't make,
oh my gosh.
right? Because otherwise that's a problem, right? So actually, I'm actually curious. Like, if you want, can you take a quick picture and show it to me or something like that? I'm curious. That because from my book, I only see the comma between 2 and the 1 minus x. So there's nothing. You say there's something here?
Yeah, mine has
Okay,
a bit
that's
of an
weird.
A.
Okay. Is that the only place that makes you confused, or like?
I don't know now because now I'm like confused on what I'm actually being asked.
So okay, so like, do you agree that P2 is a two-dimensional vector space, right? It's a polynomial space. So it should only have bases, 2 vectors as the basis, right? So you could not have 3 of them, right? So and also if it really looks like 1, 2, and this would not be a basis anyway, because 1 and 2 would be a multiple of each other. They're not linear independent, right?
Yeah.
So yeah, so it cannot be basis no matter how you view it, right? Either way. So yeah, so it's actually just 2. So it's this is V1 and V2. This is U1, U2, U3. Yeah.
I don't know what's going on there because my electronic copy does this. It says like find the matrix representation of L with respect to the ordered bases x squared, x1, and then 2, 1, negative x.
Okay, that's weird. Mine is the hard copy. That's why I don't know the online version though.
Yeah.
Because I don't own an online textbook, so mine is the hard copy. So probably like when they converted to the thing, they didn't. I don't know. Somehow I find it a little bit hard to believe that why this is true. So yeah, I mean, do not 100% believe the textbook definitely, because even sometimes the solution in the back, they could have mistake. Like, I don't know whether they fixed the problem in this version, but like I remember the previous version, the solution in the back, like they sometimes even misplace the problem. Like they put the solution for say problem 10 to problem 9, and then they miss the 10. Like there's all sort of issues sometimes. Yeah. So I mean, it happens, but I'm glad you asked, right? So it's really 2 of them. It's only 2 of them. Okay. So okay. So then let's see. So okay, so for this problem, what they do is that if you plug in a polynomial from P3, right, then the output would be the map looks like you take the derivative of this polynomial and plus whatever the value of this polynomial evaluate at 0. So for example, let me give you an example, right? If you have, say, something from P3, say maybe 2x plus 2, maybe I'm just make up some example. Like, okay, if this is your Px, then what would be L of Px? Then it means that you're taking the derivative of this function polynomial, that would be 4x plus 1, right? Plus the value P of 0. So if you plug in P of 0, that's 3. So that would be the output. That's what the map looks like. Okay. Yeah, so that's what it meant, the notation. Yeah. So now they want to say that actually you can check this should be a linear transformation. You can check that this should be yeah, it should be a linear transformation. So now let's see. Yeah, and then so now what they want for each of the following vectors in P3, find the coordinate of this with respect to the order basis. Okay, so there's several ways of solving this problem, right? So okay, let me erase this for now. Okay.
Wait, does this go back to the UV basis thing?
Yeah. So the things that, okay, let me see. There's several ways. I need to like trying to see which way is most efficient. Find the coordinate of this with respect to order basis. Okay. So yeah, so okay. So did I assign A and B, or I forgot what assign? Did I assign?
You did A for this one and then AB for 18, I believe.
Oh, okay. So A this one. Okay, I just want to make sure. Let me make a remark too, so I don't read the wrong problem. Okay, so A here.
Oh wait, would it have been more efficient to find like the transformation matrix?
Yeah, actually, the one easiest way I would think of is that then yeah, I mean there's several ways. Either you can find the matrix representation of this L, right, and then multiply by the vector you plug in. But it seems to me that the first thing I would think of is to actually, yeah, just really compute this. So let me see, that's probably the fastest way to do it. So let me see. So I have L of P of X, right? In this case, I want to plug in this matrix, this polynomial, right? So this would be derivative of this would be 2x plus 2 and plus P of 0 in this case would be minus 3, right? Yeah. And so this would be 2x minus 1, okay? So now I say this is L of P of X. I want to find the coordinate of this polynomial with respect to the basis 2 and 1 minus x, right? So in other words, you want to represent this in terms of some linear combination of 2 plus another linear combination of 1 minus x. That's it, right? This shouldn't be too hard to see it, right? Like, I mean, you need to kind of solve it. So this would be 2a plus b minus bx. So then you compare, right? You essentially say, okay, this is the constant term. So 2a plus b should be minus 1. And minus b should be 2. Actually, it's even easier than I thought. So b is minus 2, right? There's no other thing I can do to come up with an x term. So b is minus 2, then I can solve a. So 2a minus 2 equals minus 1. So 2a would be 1 and a will be 1/2. So that's double check. So 2x minus 1 should be 1/2 times 2 plus minus 2 times 1 minus x. Is that right? 1 minus 2 minus 1. Yeah. So then, because that's what we meant by coordinate with respect to the basis, right? Order basis. And you want to be careful, right? It's in this order, right? 2 first and then 1 minus x, right? So this essentially is like exactly what you said. The coordinate with respect to this basis of this vector is really just 1/2 and minus 2. In this order, right? If you flip, then it wouldn't be in the wrong order. Yeah.
Okay.
Yeah, so actually you're right. It's easier in this case. You just kind of plug in the polynomial. First, this tests you whether you actually understand the definition of this linear map, right? Then you actually see that, okay, in this case, what would be essentially you need to, this is kind of change of coordinate, right? In some sense, right? But because this problem probably is too easy, so it will be actually easier just directly find it. But there's some other way to do it in the sense that, I mean, it's probably more detour, is that you can find a matrix representation for this L, and then, you know, like for example, I mean, like there's a detour way is that if you could represent this L as like a metric representation, right? Times like your vector from the, so basically if you can find a matrix representation, right? Then you want to find a matrix representation with respect to these two bases, right? If you can do that, right? Once you found it, then you should get, so if you have anything coming from here using the basis in U, then it should, and this is the correct matrix representation between these two bases, then the output should definitely automatically give you the matrix representation of the output in V. But you can see that this way it will be detour. You need to actually first find the matrix representation. I don't think it's necessary, or I don't think it's ideal. So I think what we have done here is the most easiest and direct, because you can easily find out you can easily find out actually, oh, sorry, I misread. They actually want to find sorry.
Yeah, I think it wants us to do both.
Yeah, they actually want to do both. So actually, I'm sorry, I jumped the line. I didn't realize that they want to find the metric representation for okay. Then we need to really do the other way around. This is actually, because I was thinking that, I was actually just puzzled why they asked this question without finding the metrics. Okay, so now I read this line, find the matrix representation of L with respect to Okay, and then dot, and then next thing find each. I just jumped to the conclusion. Okay, so now, okay, then we really need to find it. So what's the matrix representation, right, for both spaces? So this would be essentially you want to plug in the first basis, right? So how many of them? U2, U3. So this is what we know about. So first you need to plug in the basis from the domain into L, right? But then because we want it to be represented in terms of specific basis, so you want to do the change of coordinate for each of them. So this would be your matrix representation. So U is the, let me recall, U is this order basis, U1, U2, and U3. And V is the 2 and 1 minus X. This is V1 and V2. So if you want to find a matrix representation of your linear transformation, you need to see first how it acts on the basis from the domain. But then since we want to, with respect to the different bases here, so then we need to change it to V. We need to do the change of coordinate because this is not the standard matrix representation anymore. This is actually with respect to these two general bases. So now let's see, right? Then this is need to do a little bit more work. So first, let's find out of U1, right? But actually, there's several ways of doing it. Either you can find L of U1 in general, right? And each of them, you represent it, like find a change of coordinate. Or actually, there's some kind of a shortcut that I mentioned at the very end last time, that in order to solve this, right? What's this? This is essentially L of U1, but you want to find this vector and then do the coordinate, change of coordinate with respect to V, right?
Yeah.
But to find this, if you think about it, then this is something we learned in 3.5. V times this whatever this vector is with respect to its like coordinate in V, it should be the same as standard basis, I call it E, times the coordinate with respect to E. But E is just identity. So actually, and this is really, if you don't do anything with respect to the vector, I mean, for the vector, then it's just the, so the original L of U1 is already the coordinate with respect to the standard basis. So what I want to say is that when you're trying to figure out this vector, this is the unknown, right? We are solving V times, if you call this B1, equals L of U1. We can find L of U1 by plugging in later on. We know what V is, right? V is this thing. Then we can actually solve B1. B1 is what we want. So here, the second column, you're essentially solving V times B2 equals L of U2. And third column would be V times B3 equals L of U3. And you can all put it all together by solving a giant like arithmetic matrix. This is something I mentioned like in the very end of, I think, this section. So what shortcut we can do is, okay, we want to solve V times something, right, equals L of U1. But in general, I only do this, right? And then you do the computation, right? If we want to solve this equation, we put it like this, right? But you can see that the process should be the same as V times B2 equals L of U2. So I want to solve these three equations all in once. So what I'm going to do is put like this, V, and the right-hand side is L of U1, L of U2, and L of U3. And we do the Gauss elimination. In the end, you should get identity here. And the right-hand side will become the B that you want. I was kind of re-explain what I did in the class. So this is the shortcut. Like you can actually solve this first column, second column, and third column, using the concept from change of coordinate. But then you essentially say, okay, instead of solving three similar equations, the process is exactly the same, right? Instead of solving three separately, I solving all in once by putting in the augmented matrix like this. So now that's C. So but I still need to find L of U1, L of U2. So that's C. So first, L of U1 is really just L of U1 is in this order x squared, right? So I'm plugging 2x, the derivative plus P of 0 is 0. And L of U2 is L of x. This is derivative plus 0. L of U3 is L of 1, which is derivative plus P of 0 in this case, because it's constant. So actually, I think this is where the problem is. A lot of people missing this one. Okay. So now, okay, so what now? So L of U1 is really, L of U1 looks like in terms of the standard basis, it's essentially 0 to 0, right? In terms of the standard basis, and L of U2 is really just 0, 0, 1, and L of U3 is 0, 0, 1. I'm using represented as the basis in U, right? Which is essentially the standard basis. Yeah. Okay. So, okay, so I'm going to put 0 to 0, 0, 0, 1, 0, 0, 1. Okay. Actually, there's several ways, right? Either you can do that. And what's V? Sorry, V is 2, which is 0, 0, 2. And 1 sorry. Wait a minute, there's something weird. Did I do something wrong? V should be in RP2. Okay, hold on. I'm confusing myself. Sorry. This is actually in the, sorry, I'm doing too fast. This is in the domain is in, this is, the image is in P2. So actually, this should be only 2 variable. Sorry. So this would be L of U1 is 2x. So that's 2, 0. Yeah. There's only 2, L of U2 should be 1, 0, 0, 1.
Wait, hold on. Why are 2 and 1 in the same? Wait, what?
Sorry. What?
Up in top left, you have a full 0 row and then 2, 1, 1 in the same row.